energy is satisfied. Okay, another example where mechanical energy can be converted to heat energy according to the law of conservation of energy. At Niagara Falls, the water drops 50 meters. If the change in potential energy goes into internal energy of water. Now remember, internal energy can be increase in potential energy or kinetic energy. Here we assume that all that potential energy goes into increasing the internal kinetic energy of the molecules of the water. That means it contributes to an increase in temperature. Only an increase in kinetic energy will contribute an increase in temperature. Alright, compute the increase in its temperature. Alright, let's consider m kilogram of water at the top of the fall. Well, I have to apologize for the shoddy diagram of the Niagara Falls that I have drawn here. Alright, we start with m kilograms of water at the top. What is the potential energy of that m kilogram of water? Its potential energy U equal to mgh. Well, so the potential energy at the top is mgh. And when it falls down all the way through 50 meters, all its potential energy will be lost. All that potential energy will become kinetic energy, or it becomes internal energy of the molecules of water. Potential energy at the bottom is 0. Therefore, the change in energy, what is the change in energy as the water reaches the bottom? Will be delta U equal to mgh. Because it started with a total energy of mgh. At the bottom, its potential energy is 0. So, the change in energy, therefore, is mgh. Now, this change in energy becomes internal heat energy. Therefore, if delta theta is the change in temperature of water, let me see if anybody remembers that. Now, if m kilogram of a substance undergoes a change in temperature of delta theta, what is the amount of heat added to the system? What amount of heat added to the system will result in a change in temperature of delta theta for a mass m if the specific heat of the system is C? Can you recall that? dQ, the amount of heat added to result in a change in temperature, will be mass times specific heat times change in temperature. And we will assume that all this dQ comes from that change in energy mgh. So this is now set equal to mgh, and therefore we can now solve for delta theta. You can see mass and mass will cancel from either side, so that will not feature in the problem. Therefore, delta theta equal to gh divided by specific heat of water. G is 9.8, H is 50 meter, H is 50 meter, and of course the specific heat of water is 4180, and that will be 0.12 Kelvin. As the water falls through a height of 50 meter, its temperature will increase by 0.12 Kelvin. You see? A direct consequence of the first law of thermodynamics. Another problem. A lead bullet, initially at 30 degrees Celsius, just melts upon striking a target. Assuming that all of the initial kinetic energy of the bullet goes into the internal energy of the bullet to raise its temperature and melt it. Can you believe that it will happen? Yes? The bullet that is moving with a tremendous velocity strikes a target, and all the kinetic energy it was carrying is now used to increase the internal energy of the bullet, which then increases its temperature and melts it. Alright? What are we supposed to find? Calculate the speed of the bullet upon impact. We have the melting point of lead is 327 degrees Celsius. Latent heat of fusion for lead is 2.47 times 10 to the 4 joules per kilogram, and specific heat of lead is 128 joules per kilogram per Kelvin. Alright, now how do we apply the law of conservation of energy, or the first law of thermodynamics here? Well, the moving bullet has a kinetic energy. What is the kinetic energy of the bullet that has a mass m and a speed v? It'll be 1/2 mv squared. And all that energy is going to become a quantity of heat. And what is that quantity of heat going to do? That quantity of heat, first of all, increases the temperature of the bullet from 37 degrees to 327 degrees. Now tell me, what is the amount of heat needed to do that? To increase the temperature of the lead bullet from 30 degrees Celsius to 327 degrees Celsius. It will be mass times specific heat times change in temperature. Now, is that all? No. After increasing the temperature to 327 degrees Celsius, it is then converted from solid to liquid lead at the same temperature. There is a change of state. The amount of heat used to do that will be mass times latent heat of fusion. That means, you can see I'm doing this problem in mind, and you must actually practice doing this kind of thinking. All the energy that the bullet carried, 1/2 mv squared, has become internal heat energy, and that heat energy is used in two ways. First, mc delta theta to increase the temperature from 30 degrees to 327, plus mlf, mass times latent heat to fusion, to convert lead from solid to liquid. Alright, let's write these things down. Let the speed of the bullet be v and its mass be m. The kinetic energy K upon impact then will be K equal to 1/2 mv squared. Alright? This energy is used. All this energy is used to increase the internal energy. So all this has now become heat. Raise the temperature of the bullet to its melting point of 327 degrees and then melt it. Alright, we have all this data which we can use for that problem. That means 1/2 mv squared, that is the total quantity of heat. All that mechanical energy is now converted to heat. And that heat is used to increase the temperature of the bullet. Mass times specific heat times change in temperature, plus change the lead from solid to liquid without changing its temperature. Mass times latent heat of fusion. And you notice mass will cancel from everywhere. You don't need the mass of the bullet to do this problem. Alright? That means 1/2 v squared equal to specific heat of lead is 128, and delta theta is 327 minus 30, plus latent heat of fusion is given to be 2.47 times 10 to the 4. Notice again that the mass has cancelled from each term. And now the only unknown quantity is V. You can solve for that. The right hand side simplifies to 62,716, and that is 1/2 v squared. Therefore v squared is double this, and therefore v is the square root of that, and that is 354 meter per second. Okay, let's